Can you all hear me? Okay. All right. Thank you, Andy, for the introduction, and good morning, everybody. So like Andy said, I've been working on this project for the past 3 years, and it's been working with effects of potassium source and rate on yield, quality, and leaf chemistry of dark and burley tobacco. And then I had another project that works with residual effects of soil potassium levels. Okay, so this is a little bit of an outline of what we're going to talk about today. So first, we're going to go over the overview of potassium fertilizer here in Kentucky. We're also going to have a little bit of an overview of, about what tobacco-specific nitrosamines are. We're going to talk about some of the abbreviations that I'm going to use. I have a lot in this presentation, so I wanted to go ahead and address them up front so it's easier for you all to identify what I'm talking about. Then we're going to go into Chapter 1, which is my field study. So we're going to talk about the objectives of that study. Then we're going to move into the 2016 materials and methods and results, followed by 2017 and 2018 materials and methods and results. And then we will have conclusions for each of those years, 2016, 17, and 18. Then we're going to look at Chapter 2, which is my bare ground study, we've called it, which is looking at those residual potassium levels in the soil. We'll have overall conclusions, and then we'll have acknowledgments and then questions. Okay, so a little bit of potassium fertilizer here in Kentucky. So Kentucky actually has a Kentucky Fertilize Law that regulates farmers from applying no more than 123 pounds of potassium chloride to tobacco ground after January 1st, or that is approximately 56 pounds of actual chloride per hectare to tobacco ground. So because of this Fertilize Law, many farmers are applying potassium chloride in the fall of the year, but also due to the fact that potassium sulfate is approximately 30 to 50% cheaper, potassium sulfate is 30 to 50% more expensive than potassium chloride is. A little bit more about potassium fertilizer. So we have two major potassium fertilizer sources here in Kentucky. That is potassium sulfate, or 0050, and then potassium chloride, or 0060. So a little bit more specifically about potassium chloride. So potassium chloride has actually been shown to detrimentally impact leaf quality when it's used in the spring of the year on tobacco ground. So if you have higher than a 1% chloride in the cured leaf, you can have a higher moisture content, and you can have a bad aroma or poor burning characteristics in combustible products such as cigarettes. So now a little bit about tobacco-specific nitrosamines, or TSNAs, is how they'll be abbreviated in this presentation. So TSNAs are formed from tobacco alkaloids that are found within tobacco leaves. Okay, so these are produced primarily during the curing process, but they can be found at minute levels in freshly harvested tobacco. So some of these TSNAs are known carcinogens. And in tobacco production, we have 4 major TSNAs that we look at. I cannot pronounce these big long names, so I'm going to give you all the abbreviations. We have NNN, NNK, NAT, and NAB. Okay, so some of the analysis that we have conducted in this project for the past 3 years, we looked at the yield, we looked at moisture, chloride, grade index, and TSNA data. So all of our leaf chemistry analysis as far as the chloride, the moisture, and the TSNA data was all conducted by R.J. Reynolds Tobacco Company. And this data analysis was done by using SAS version 9.4 using an alpha of 0.1 as significant. Okay, now for abbreviations that we're going to be using. So we're going to be talking about dark air cured, and that's going to be abbreviated by DAC. Dark fire cured is going to be abbreviated by DFC. K2SO4 is going to stand for potassium sulfate. KCl is going to stand for potassium chloride. CL is going to stand for chloride. K is going to stand for potassium. And then what we had just discussed, TSNA is going to stand for tobacco-specific nitrosamines. And then GI is going to stand for quality grade index. So our grade index is we have a federal tobacco grader that comes out and grades our plot. They give that a code, and then that code is then translated into a numerical value. So then that is averaged over all of the stalk positions, and that grade is given for that plot. Okay, now we're going to be talking about the objectives of my field trial. So the objectives for all 3 years is we wanted to determine if potassium source and application rate, has an effect on the yield and the leaf quality in dark tobacco as well as in Burleigh tobacco. We also wanted to evaluate the effect of potassium source and application rates on chloride and TSNA levels. Okay, so now we're going to talk about the 2016 materials and methods. So in 2016, we only had one location, and that was at Princeton, Kentucky. But at that one location, we did have two trials. We had a dark air cure trial and a dark fire cure trial. We only had one variety in 2016, and that was KTD14LC. These plots were transplanted on May 25th, and then they were harvested on August 23rd. So more about the materials and methods for 2016. We did use the two major potassium sources that are available here in Kentucky for this trial. So we used potassium chloride and potassium sulfate. We did have 3 application rates of these two sources, 112, 224, and 336 kilograms per hectare. We also had an untreated control that received 0 potassium. Our plot design for 2016 was a randomized complete block, and we had 4 replications. Phosphorus and nitrogen were applied according to soil test recommendations, and then all other field management followed the University of Kentucky Extension recommendations. Okay, so now we're going to be moving into 2016 results. So this is how my field looked 3 times in 2016. So if you're a farmer, this is not something that you want to walk out one day and see your crop look like. And it looked like this because of the above average rainfall that we had in 2016. So here on the x-axis, you have your months. On the y-axis, you have your precipitation. Your blue line is the rainfall per month, and the gray line is the 30-year average. So you can see here that we had above rainfall in May, July, and August, which is during the growing season for tobacco. And as you see here in the below the legend, you can see that the monthly precipitation added up to be 142 centimeters, and then the 30-year average was 128 centimeters. So we had 14 more inches of rain in 2016 than the average had been. So with this above precipitation that we had, we're going to see less effects in this 2016 trial because there was more variability in the plots because of the severe weather that we had. So now looking at the results. So this is for the dark air cured trial, 2016. We had an effect of source for the percent moisture and also an effective source for the percent chloride. Okay, so you have your 2 sources here on the bottom. You have potassium chloride and potassium sulfate, and you have your percent moisture or percent chloride here on your y-axis. The blue bars represent the moisture content, and the gray bars represent the chloride content. Okay, so you can see here that for both moisture and chloride, potassium chloride treatments had a higher moisture content and higher chloride contents compared to tobacco that was treated with potassium sulfate. Okay, so now we're looking at a 2016 dark fire cured trial, and here we had an interaction for source and rate for the percent of chloride in the cured leaf. So I'm going to be showing interactions in 2-way tables. So these 2-way tables are going to be set up. I'm going to have rate on the side, and source is going to go across the top like here. And then everything that you see here in red is significant. Okay, so as we expected, the percent chloride was higher in tobacco that received potassium chloride and was highest in tobacco that received the 2 highest rates of potassium chloride at that 224 kilograms per hectare and the 336 kilograms per hectare. Okay, so for our dark fire cured trial, we had an effective source for TSNA levels. So here we saw that tobacco that was treated with potassium sulfate, and this is averaged over rates, tobacco treated with potassium sulfate had higher TSNA levels than tobacco that was treated with potassium chloride. Okay, so that was 2016. Like I said, we didn't have a lot of differences in 2016, which can be contributed to that weather. So moving on to 2017. So 2017, like Andy stated, my project got changed a little bit. We added some locations and a variety. So in 2017, we still use those 2 potassium sources, potassium chloride and potassium sulfate. We did keep the same 3 application rates, 112, 224, and 336 kilograms per hectare, and also an untreated control. For the varieties, for the dark air cured and the dark fire cured trial, we kept that KTD14 LC variety, but we also added the narrowleaf medulla high converter variety. We also added a Burleigh trial. So for our Burleigh varieties, we used Tennessee 90 LC and Tennessee 90 HC. So we added in this high converter just so that we could see differences in TSNA levels easier. Low converter varieties are the only varieties on the market for farmers to grow. So we incorporated this high converter in just so it's easier for us to determine if there's differences in rates or sources in TSNA levels. Also, our plot design did change in 2017. We went from a randomized complete block design in 2016 to a split plot design in 2017. We did keep the 4 replications. For our dark trials, we had 4 rows that were 4 meters wide by 12.2 meters long, and our Burleigh trials were 4 rows, 4.1 meters wide by 10.6 meters long. Okay, so we kept that Princeton location that we used back in 2016, but we also added a Murray location and a Lexington location. So at the Princeton and the Murray location, there was both a dark air cured trial and a dark fire cured trial. In the Lexington location, there was only a Burleigh trial. Okay, so just like in 2016, phosphorus and nitrogen was applied according to the soil test recommendations, and all other field management followed University of Kentucky recommendations. So 2017 transplant and harvest dates. So in Princeton, these were transplanted May 26th, harvested September 21st. At Murray, transplanted June 21st and harvested October 12th. Lexington, transplanted June 13th and harvested September 8th. So you might see here that the Princeton and the Murray location, these trials were left in the field just a little bit longer than what the Lexington location is. And that's just due to dark tobacco being left in the field for approximately 6 weeks after topping before it's harvested. And then Burleigh tobacco is left in the field for approximately 4 to 5 weeks after topping before it's harvested. So that's why you might see a difference in Lexington being in the field for a shorter time. Okay, so now we're going to go into 2017 dark tobacco results. So there is a lot of results here. So we're first going to start out talking about yield, then we're going to move to moisture, we're going to talk about grade index, and then TSNA. Okay, so for the dark fire cured trial, we had an effective location for yield. So you can see here that our Princeton location, when averaged over source and rate, had a higher yield compared to the Murray location. For our dark air cured trial, we had an effective variety for yield. So when this was averaged over location, over source, and over rate, we saw that the low converter variety had a higher yield than our high converter variety did. Okay, here's another two-way table. Again, my rates are on the side, my sources are across the top. So here we had, for our dark air cured trial, we had an interaction for source and rate. So this is averaged over location. And we saw here that at the 112 kilograms potassium sulfate, or at 112 kilograms potassium sulfate, there was a higher yield compared to potassium chloride. When you look at the 224 kilograms of potassium chloride, actually had a higher yield than potassium sulfate did. So then if you look at the 336 kilograms of potassium per hectare, we see that potassium chloride again had a higher yield than what potassium sulfate did. So if you see, as you increase your rate here of potassium chloride, you actually increase your yield. That's vice versa for sulfate here. As you increase your yield, you decrease your yield. As you increase your rate, you decrease your yield. Okay, so here's a dark fire cure. This is interaction of location and variety for the percent of moisture that we had. So at the Princeton location, the low converter selection had a higher moisture percentage than the high converter selection did. So I didn't state this earlier, but where we had KTD14 LC, from here on out, that's going to be indicated as LC on all of these graphs. The narrowleaf medulla high converter is going to be indicated by HC on all of the graphs. Okay, so for the dark air cure trial, we had an effective location for the percent moisture. So this is averaged over rate and source. And we saw here that our Princeton location had a higher moisture percentage than what our Murray location did. For our dark air cure trial, we had an effective variety for percent moisture. So here we saw that our low converter variety had a higher percent moisture than our high converter variety did. Okay, so we had an interaction for our dark air cure trial in 2017, and we had a location by variety interaction for grade index. So here you can see that at Princeton, the low converter variety had a higher grade index than the high converter variety. And across both varieties, Princeton tobacco had a higher grade index than the Murray plots did. Okay, for our 2017 dark air cured, we had an effective source for grade index, so this is averaged over location and rate. So here we see that plots that received potassium chloride as the potassium source had a higher grade index compared to plots that received potassium sulfate as the potassium source. Okay, here we had a four-way interaction for our Darkfire cure trial. So we had a location, by source, by rate, by variety interaction for this trial. So this is going to be broken down by location. So you can see here we have Princeton at the top and Murray at the bottom, and then it's broken down again by low converter or high converter, and the same for Murray here. Okay, so within the Princeton low converter, at the 224 kilograms of potassium per hectare rate, the grade index was higher in tobacco that was treated with potassium chloride. The grade index generally increased with increasing potassium rates from both potassium sources, whether it be potassium chloride or potassium sulfate, they increased. So then there was no differences in the Princeton high converter selection, but if you look at the Murray low converter selection, grade index was higher in tobacco that was treated with potassium chloride at 112 and 336 kilograms of potassium per hectare. Then if you move down to the Murray high converter selection, tobacco treated with potassium chloride at that 112 and 224 kilograms per hectare had a higher grade index than tobacco that was treated with the same rates of potassium sulfate. So within this sulfate treatments in the high converter selection, the grade index was highest at the 336 kilograms of potassium per hectare. Okay, so we have a three-way interaction here, and this is for the Darkfire cure trial. This is a location by source by variety interaction, and this is for TSNA data. So for both of these locations, for Princeton and Murray here, they're still split out from each other. The narrowleaf Madol high converter had the highest tobacco-specific nitrosamines compared to the low converter variety, which is not uncommon to see. High converter varieties do have more TSNA levels than low converter varieties is, so this is a given when you go to run your data analysis. But tobacco that received potassium sulfate treatments actually had higher TSNA levels compared to tobacco that received potassium chloride as the potassium source. Okay, so we had another four-way interaction for our dark air cure trial, and that was location, by source, by rate, by variety. Okay, so this is still separated out by location. You have your two Princeton locations at the top, two Murray at the bottom, and then separated out between high and low converter. So within the Princeton high converter, TSNAs were lower in potassium chloride treated tobacco. Within the Princeton low converter variety treated with potassium sulfate, they had higher TSNAs. And TSNAs generally increased as that potassium sulfate rate increased. The Murray high converter selection, potassium sulfate treatments, had higher TSNAs compared to potassium chloride treatments at that 112 kilograms of potassium per hectare. And then TSNAs decreased with increasing rates of potassium chloride. Moving on to the Murray low converter variety. The Murray low converter, you had decreased TSNAs with potassium chloride treated tobacco. It was not as strong as what we had been seeing in the other locations in the other trials, but it's not as strong, but the trends were still apparent in this 112 kilograms of potassium per hectare. Okay, so that is the dark study. So now we're going to be moving into 2017 Burleigh results. So here we're going to kind of follow the same trend. We're going to talk about yield first, then followed by moisture, then followed by TSNA. So for 2017 Burleigh, we had an effective variety for yield. So here we saw that our low converter variety actually had higher yield than what our high converter variety did. And ignore this, I just saw this. This says TSNA, that's incorrect, that should be yield. Okay, so still for Burleigh 2017, we had an interaction for source and rate for the yield. So here we saw that within the 112 kilograms of potassium per hectare rate, yield was higher in tobacco that received potassium sulfate. So within these potassium sulfate treatments here, as you increased your rate of potassium, you decrease, or as you increase your rate of potassium, you see that your lowest yield is from that 336 kilograms of potassium per hectare at that 2,696. Okay, so still talking about Burleigh. So here we had a three-way interaction of source, rate, and variety for the percent moisture. So here you see this is separated out by variety. So here's your low converter on top and your high converter on the bottom. And you see here that within the potassium sulfate treatments for the low converter selection, which is right here, you see that there's a higher moisture that was observed in tobacco that received the higher two rates, that 224 and 336 kilograms of potassium per hectare. Okay, so then if you move down to the high converter variety that you see, moisture levels were higher in potassium sulfate when it was applied at 112 kilograms of potassium per hectare. And the highest within the larger two rates that you apply, the 224 or the 336 kilograms of potassium per hectare of potassium chloride. Okay, so then we had an effective source on TSNA levels. So here we saw, again, like what we saw earlier in the dark trials, tobacco that was treated with this potassium sulfate as the potassium source had higher TSNA levels than tobacco that was treated with potassium chloride as the potassium source. We also had an effective rate on TSNA levels. So here is your rates at the bottom, the 112, 224, and 336. So you can see here that there is a difference between your 224 and your 336 kilograms potassium applied per hectare. So in your 336, you have higher TSNA levels compared to this 224. We also had an effective variety for TSNA, which, like I said, is not uncommon. High converter varieties do have higher TSNAs than low converter varieties, which is what you see here. Higher TSNAs in the high converter rather than the low converter. Okay, so that's 2017. So we're moving on to 2018. So 2018 materials and methods are pretty much identical to, or they are identical to the 2017 materials and methods. I'm just going to go over them again just to give you all just a brief relapse of what they were. So we still use potassium chloride and potassium sulfate as the two potassium sources. Still use the same three rates, 112, 224, and 336 kilograms per hectare. Kept that untreated control. Same varieties, we use both the low converter and high converter in the dark trials and in the Burleigh trials. For our plot design, again, was a split plot design with 4 replications. Okay, we still kept those 3 locations, Princeton, Murray, and Lexington. Dark air cured and fire cured was both at Murray and in Princeton. And again, phosphorus and nitrogen was applied according to soil test recommendations, and then all other field management followed University of Kentucky guidelines. Okay, for our transplanting dates, at Princeton, we transplanted these plots on May 24th and harvested on September 12th. For Murray, we transplanted these on June 20th and harvested them October 19th. Lexington, we transplanted these on June 19th and harvested them on September 21st. Again, keep that in mind if you're wondering about the dates there. Darkback is left in the field for a little bit longer after topping than Burleigh is. So we're going to follow the same thing that we did for 2017 dark trials. We're going to talk about yield, moisture, chloride, grade index, and TSNA. Okay, so here we had an interaction in the Darkfire cured trial for yield. So for yields, for both varieties were higher at the Princeton location compared to the Murray location. and the low converter variety yielded higher than the high converter variety did at both of those locations, both at Princeton and at Murray. So we saw an effective variety for yield. So here we saw that the low converter variety had a higher yield than the high converter variety did. So for the Darkfire cure trial, we saw an effective variety for the percent moisture in the cured leaf. So here we saw that the low converter variety had a higher percent moisture than your high converter variety did. Okay, so for our 2018 dark trial, we had an interaction for location, rate, and variety for the percent of moisture here. So within each potassium rate at both Princeton and at Murray, the low converter variety had higher percent moisture than the high converter variety did for both of these locations, both Princeton and Murray. So for the Darkfire cure trial in 2018, we had a three-way interaction of location, source, and rate for the percent of chloride. So I know this is a lot of numbers, it's a lot of red, but it's pretty easy to explain. As we expected, tobacco that was treated with potassium chloride had higher chloride levels than what potassium sulfate did. As you increase that potassium chloride level, you actually increase the level of chloride in the cured leaf. Okay, so for our 2018 dark air cured, we had an interaction of source and rate for percent chloride. So this goes along the same thing that I was just talking about. Our potassium chlorides had a higher percent chloride in the cured leaf compared to potassium sulfate treated tobacco. And as that rate of potassium chloride increased, you increased your percent chloride in the cured leaf. For our 2018 Darkfire cured trial, we had an effective location for grade index. So here we saw that the Murray location actually had a higher grade index compared to the Princeton location. For the Darkfire cured trial, we had an interaction of location and variety for TSNA levels. So TSNA levels were higher in the high converter variety, which is what we already know, but they were also higher at the Princeton location compared to the Murray location in that low converter variety. So in the low converter variety, they were higher at Princeton TSNA levels than they were at Murray. Okay, so for the 2018 dark air cured, we had an interaction of location, source, rate, and variety. Okay, so TSNAs were numerically lower in most cases where tobacco was treated with potassium chloride, but these differences were only significant at the 112 kilograms of potassium per hectare and at 336 kilograms of potassium per hectare at the Princeton location with the high converter, and then at 336 kilograms of potassium per hectare in the low converter variety at Princeton. And there was no differences in the Murray high converter selection, so we'll skip to the Murray low converter selection. And we see here that at the 112 kilograms potassium rate, and the 112 kilograms potassium per hectare rate, and the low converter variety at Murray had higher TSNA levels compared to the potassium chloride treatment. Okay, so now we're moving into the 2018 Burleigh results. So again, yield, moisture, chloride, TSNA. So for the Burleigh trial, we saw an effective source for yield. So here we saw that treatments that received potassium chloride as the potassium source had a higher yield than what treatments that received potassium sulfate did. We also saw an effect of moisture, we also saw an effective source for percent moisture. So here we saw that treatments that received potassium sulfate as the potassium source had a higher moisture content than what treatments that received potassium chloride did. We also saw an effective source for the percent chloride, which goes along what I've been talking about. Obviously, potassium chloride treatments had higher chloride levels than potassium sulfate treatments. Okay, so now we're going to look at the Burleigh 2018. We had an effective source and variety for TSNA levels. So this graph here, you have your TSNA levels on the side. Here you have potassium source, and on this side you have the variety. So when you look at the two potassium sources, potassium sulfate, again, it follows the same trends that we've been seeing, has higher total TSNA levels than potassium chloride treatments. And again, this is known, the high converter variety had higher TSNA levels than the low converter variety did. Okay, so now we're going to go into the conclusions. So these conclusions are broken up into years. So we're going to start with 2016. So in 2016, we had an effective potassium source in the dark air cure trial for the moisture and the chloride content in the cured leaves. We had an interaction of source and rate for chloride levels in the Darkfire cure trial. So, like I said, potassium chloride treatments, higher chloride levels, increase in chloride, increase your chloride levels. But we didn't see many differences in 2016, like I said, so severe weather may have increased the variability in these plots, and that's why we saw less differences than we saw in 2017 and 2018. Okay, I know this is a lot of stuff on this slide, but this is the conclusions for the dark tobacco trial. So this is broken into yield, moisture, grade index, and TSNA. And then under each of those, it's broken into air cured or fire cured. So for the dark air cured trial, for yield, the low converter variety had a higher yield when it was averaged over location. We had a source by rate interaction. So you had an increase of potassium chloride rate, your yield increases, and that was vice versa for potassium sulfate treatments. So as you increase your rate of potassium sulfate, you actually decrease your yield. So moving on to moisture, for our dark fire cure trial, we had a location by source interaction. So for our Princeton low converter variety, it had the highest moisture content. For our dark air cure trial, we had an effective variety. So our low converter variety had the highest moisture content. Grade index, for our dark air cure trial, we had an interaction for location and variety. For our Princeton low converter variety had the highest grade index, and then Princeton had a higher grade index than Murray overall. Moving on to TSNAs. So for both the dark fire cure and the dark air cure trial, both locations obviously had higher TSNA levels in the high converter variety, and they had higher TSNA levels in treatments that received potassium sulfate as the potassium source. Okay, so now we're going to be looking at the 2017 Burleigh results. So again, broken into yield, moisture, and TSNA levels. So for yield, we had an effective variety. That low converter actually had a higher yield than the high converter variety did. For moisture, we had a source by rate by variety interaction. So we had a higher moisture that was observed in the two highest rates of potassium chloride and potassium sulfate for both of those varieties. For TSNA, potassium sulfate treatments had higher TSNAs, which follows the same trends. We had an effective rate. 336 kilograms potassium per hectare had higher TSNAs than the 224 kilograms potassium per hectare. We did have an effective variety for TSNA, which is a given. The high converter variety had higher TSNA levels than the low converter variety did. Now to talk about the 2018 dark tobacco conclusions. So again, yield, moisture, chloride, grade index, and TSNA. So in yield for our dark fire cure trial, we had a variety by location interaction. So yield was highest at the Princeton location, and then the low converter variety had higher yields than the high converter variety did. So if we look at the moisture, in the dark fire cure trial, we had an effective variety. The low converter variety did have a higher moisture than what the high converter variety did. For our dark air cure trial, we had a location by rate by variety interaction. So here we saw that within each potassium rate at both of those locations, the low converter variety had a higher percent moisture than the high converter variety did. If you look at the chloride, for both the dark fire cured and dark air cured, both locations, potassium chloride had higher chloride levels and generally increased with the application rate. For grade index, for our dark fire cure trial, we had a location effect. Murray had a higher grade index than what Princeton did. For our TSNAs, dark fire cure trial, we had a location by variety interaction, and our high converter variety did have higher TSNAs. And then the Princeton location had a higher TSNA levels for both varieties compared to Murray. For dark air cured, within each potassium rate at both Princeton and Murray locations, the low converter variety had a higher percent or had higher TSNA levels. The high converter selection at both of those locations, at both Princeton and Murray, had higher TSNA levels than the low converter variety. Okay, so Burleigh conclusions. So for our yield, we had an effective source. So potassium chloride had a higher yield compared to tobacco that was treated with potassium sulfate. Moisture, we also had an effective source. Potassium sulfate treatments had a higher moisture content than potassium chloride treatments. For chloride levels, we had an effective source. Potassium chloride had higher chloride levels, obviously. And then TSNA, we had an effective source and variety. Potassium sulfate treatments had higher TSNA levels. And then the high converter variety, again, had higher TSNA levels than the low converter variety did. Okay, so now we're going to be talking about my bare ground study. Well, this is what we called it. So this is the study where we look at residual potassium in the soil. So the objective of this study is we had talked to some farmers and we had talked to some county agents, and they had farmers that were going out and they were applying potassium chloride in the fall of the year, or they were going out in the fall of the year and they were soil sampling and applying potassium chloride at that recommended rate that they got back from their soil sample. But then if they went back and they soil sampled again the following spring, that soil test still recommended some potassium to be applied. So for this reason, we wanted to establish these field trials to monitor how these soil potassium levels change over time following fall potassium applications. So some materials and methods for this bare ground study. So these sites were established December of 2016. And for all of these sites, the initial soil K levels were less than 224 kilograms per hectare. We had 2 sites at Princeton and 1 at Murray. Our soil types at Princeton were Kreider and Zanesville. And then for our Murray, we had a Grenada soil type. So for all 3 of these, there was previous crops on them. So for our Kreider, we had a corn crop on it previously. For our Zanesville, had fescue on it previously, and Grenada was just Bermuda grass. So we did keep these plots bare. When vegetation started to grow, we would go out there and we would spray it to kill off the vegetation so there would be no uptake of this potassium. So this was a randomized complete block design with 4 replications, and they were 1.5 meters by 1.5 meters. So the potassium sources that we used here were, again, potassium chloride and potassium sulfate, but we added in a potassium chloride at 2 times the rate. So we went in and we soil sampled and we got an initial soil sample for all 3 of these sites. We then applied according to soil test recommendations for all sources and rates, and also we added that potassium chloride at 2 times the rate. So we went in and we soil sampled every 3 months for 2 years. We took 5 soil samples per 1.5 meter block. They were 15.2 centimeters wide. And then at the 2-year sampling, we actually split that core. We split the 15.24 centimeter core in half. Okay, so with this information, we then wanted to look at different particle size analysis. So I worked with Yvonne Thompson and Dr. Karathanesis' lab on doing this, and here we saw that for both of those Princeton locations, the Zanesville and the Kreider, for both of the different soil depths, they were all silt loams. Okay, so then we went and we looked at the Murray location and the Grenada soil type, and they were still a silt loam. So all 3 soil types, the textural class was silt loam. So then we wanted to look into clay mineralogy. Okay, so we did this for all 3 soil types. This is just split up into 3 separate graphs because it was too big to put on one table. So here you have your location, you have your soil type, you have your previous crop, and then the depth of the soil sample. So you had your 0 to 15 centimeter and then your 15 to 30 centimeter. Okay, so these minerals didn't really vary upon if there was more certain minerals in the top section versus minerals in the bottom section, although feldspar was only found at the deeper soil sampling depth for this soil type. Okay, so this is for the Zanesville. At the Princeton location, the prior crop was fescue. So again, it's split up into 2 different depths. And here again, you don't really have a lot of variation between clay minerals within each of those soil depths, but you do have interstratified minerals in your lower soil sample depth that you do not have at your top depth. Okay, this is looking at Grenada. So here, Grenada, you actually have interstratified in the top half of your sample. Unlike in the Zanesville, it was in the bottom half of your sample. And for all of these, if you noticed, smectite was only in the Kreider soil type. Smectite was not in the Zanesville or this Grenada soil type. Okay, so for those soil samples that we took every 3 months for 2 years, this is them plotted out on a graph. You have your pounds of potassium per hectare over here, and you have your sampling times in months. So we sampled every 3 months here. As you can see here, at your 9-month sampling date, you have a drastic decrease in soil potassium level in the potassium chloride treatments at 2 times that rate. You also have another decrease at the 18 months for that potassium chloride at 2 times the rate. Okay, you have the same effect here. So at your 9 months, you have a decrease in this potassium chloride at 2 times the rate, and you also have it again at the 18-month sampling date. So it might be that potassium chloride, or that these 2 soil types is more affected by potassium chloride than just potassium chloride at 2 times the rate, rather than potassium chloride at the recommended rate or potassium sulfate. Okay, so if you look at the Grenada, which was the 3rd soil type here, you don't see as drastic of a decrease at the 9-month and the 18-month sampling as what you did for the other 2 soil types. So this might be contributed to it's less responsive to potassium. It's less variable compared to the other 2 soil types, the Kreider and the Zanesville. The potassium chloride at the recommended rate had higher potassium levels than potassium chloride at 2 times the rate in the other 2 soil samples, or in the other 2 soil types. Okay, so like I said, for that 2-year sampling, we split this into in half. So we had an interaction for soil type and depth for actual potassium levels. So here we saw that soil K was highest in the Kreider and the Grenada at the smallest depth, that 0 to 7.5, and highest in Zanesville at the deepest depth, that 7.5 to 15 centimeters. And then for the 0.75, the highest potassium level was in the Kreider, and also it was in the Kreider for the 7.5 to 15 soil depth sample. So bare ground conclusions, all of these soil types were silt loam. The KCl at 2 times the rate seemed to have more of an impact on soil K levels and the Kreider and the Zanesville compared to the Grenada. Soil K was highest in the Kreider and the Grenada at the smallest sampling depths, and then highest in the Zanesville at the deepest depth. Kreider had the highest soil K level at both of the different sampling depths. Okay, so the big picture of what these 2 projects have been working with for the past 3 years for the field study, 2 years for the bare ground study. So majority of the time, all 3 years, we're seeing that potassium chloride seem to have overall lower TSNA levels than potassium sulfate treatments. So this might be due to the chloride. It may increase the salinity in the plant and therefore reduce that nitrate to nitrite conversion. And then for our bare ground study, the soil K is influenced variably with different potassium sources for different soil types. So seasonal temperature and precipitation fluctuations may have a role in why we're seeing those drastic changes at that 9 and 18 months for the Kreider and the Zanesville soil type. We're not seeing it in the Grenada. And with that, I have so many people to thank for the past 3 years. I have my advisor, Andy, and then my committee members, Bob and Edwin. They've helped me tremendously over the past 3 years, have taught me more than I ever thought I could know about tobacco and soil. I would also like to thank RJ Reynolds Tobacco Company for sponsoring this project for my master's for the past 3 years and also for the assistantship. I would also like to thank Dr. Karathanesis' lab, specifically Yvonne Thompson, for helping me do all of these soil particle analysis and clay mineralogy samples. I would also like to thank Dr. Chris Shepard for helping me interpret those clay minerals, since I waited probably a year after me and Yvonne had worked on those to actually write this up. So I thank Dr. Shepard for that. And I would also like to thank Eric, Catherine, and Patrick for all of their help with my statistical analysis. They've been phenomenal at helping me and explaining how to run SAS. I would also like to thank Mitchell and Chris and Vicky and Bobby and Jack for all of their help in taking all these samples, all the soil samples, spreading all this fertilizer by hand. They've been a great help over the past 3 years. And I would also like to thank my parents and my brother for all their support for the past 3 years. If it wasn't for them, I wouldn't be here. So with that, I'll answer any questions. Yes, Anne. Mm-hmm. Yes, they are 2 different varieties. Mm-hmm. Yes. Yes, that is correct. Yeah, I should have specified that the low converter and high converter are 2 different varieties. So when you look at yield, you can't just say, okay, well, the low converter did have higher yields. They are 2 separate varieties. You do have to look at them like that. Yeah. Mm-hmm. Yes, that's correct. Yes, Emily.
So in your chapter 1, it didn't show 0 treatment.
Yes.
For any of these.
That is correct. So we compared to the other ones. So when I ran all this statistical analysis, I had someone from the stats department help me, and he told me to run this without the untreated control because it has nothing to compare itself to. So that would be something that we could look into to see if there was differences in that 0 rate that didn't receive any potassium compared to the 112, 224, and 336. That is something we could look at. But for this, he told me that since there's nothing else for the check to compare itself to, that we didn't need to include it in the data analysis. That's what I said. Or you can do that, yeah. Yeah. Yeah, because we did. Yeah, there's only one check.
So I guess another question that I have is, what is the recommended amount of potassium be applied in, extension station? How did your soil test compare to that in each experiment? Or differences in the, I guess, recommended rate?
Yeah, so in this field study, we did not have any treatments that actually called for the recommended rate of potassium for that specific site for any of the trials. We only did it at the 112, 224, and 336 kilograms per hectare. And all of this was either applied either one day or a week before transplanting, so it was applied after January 1st, obviously. So, like I said, the Kentucky Fertilize Law regulates farmers from applying no more than 123 pounds of potassium chloride after January 1st, and I was applying 336. So if we were to repeat this, I would recommend having a grower standard of like what the soil test was, to have that, and then try these other 3 rates to see what the differences would be there. Does that answer your question?
It would fall within that rate.
Yes, yeah, yes. And
And your moisture rate for around 6% is quite dry. So what's the percentage of the moisture?
so we took these down from the barn in 2017 and 18. We destemmed them and then we shipped them to RJ Reynolds. So the moisture analysis was ran when these samples got to RJ Reynolds. So it was probably 3 days after we had destemmed the plants. Yes, they were air dried prior to shipping.
I wonder if that's relevant because normally you would measure moisture at that time.
Okay.
Once it's been air dried, I think
Okay. Yes, Colin.
I'll go one step further and say that when you're clearing waste like that,
Mm-hmm.
they ought to be equilibrated at a, generally speaking, 21 degrees centigrade and 6% humidity. That's the standard practice.
Okay.
So even if you don't have that equipment, it ought to be that equilibrated at 8% humidity.
To get a true moisture percentage from takedown?
Yeah.
Okay.
Yeah. And I mean, the comparison of the comparison of the moisture between Murray and Princeton was
Yes.
1.6.
Yeah.
That's really irrelevant.
Okay. Okay. Okay, that's a good idea to keep in mind if this project keeps going on after I'm finished. Yes, Bob.
So this relatively consistent.
Mm-hmm. Yes.
No history.
Mm-hmm. Yes. Yes, they are.
So what would you recommend to the industry?
I mean, all you can do is present the data that you do have. I mean, like this project, we can submit it to industries, to the FDA to see what they say about this. But I mean, they're not going to take a whole 3 years of data and be like, okay, well, we need to change all of this stuff. It'll take many consecutive years, many different trials to make any progress in what Bob's talking about as far as these TSNA levels in the tobacco products. Yes, Anne.
I was rather baffled. Now, my knowledge of soil chemistry is not good. But I was baffled by the red drop study with a double ratio of potassium chloride.
Yes.
It's down with 9 months and then shot up again.
Yes, that is correct.
I can't understand that.
So that's something that we are trying to look into and determine. It could be due to temperature and precipitation fluctuations throughout the year. Like if there was a lot of rainfall, if it was really dry.